So here we have another case where we're giving a sphere with a free stream velocity of 20 meters per second prescribed to this left surface, two inviscid walls on the top. The sphere has a diameter of about a meter, and it has an outlet. Here the domain is set 8 diameters upstream, about 24 downstream, and 8 in the vertical and in both directions vertically. So how do we do this? Here we have our star simulation. What we need to do is develop our cookie cutters. What I'm going to do is, actually not here, I'm going to come. So what I'm going to do is make a part, make our sphere. It's going to be at the origin with a radius of 5 meters. If we come to this panel here, we go to geometry, we can see we have a 1 meter diameter sphere. Then we could come and make a block. And what I'm going to make is it go in the negative direction by 8, positive direction 24, negative y minus 8, and z minus 8. Positive y, positive 8, positive z, positive 8. So I'll hit create, close, because I created it twice. Keep doing that in these videos. But what you can see is a block that's 8 in all directions, but 24 downstream. So similar to the previous things, what we want to do is go to the surfaces, right click here. And because it's a block, I'm just going to split all surfaces by 89 degrees. And I call this low wall inlet. It gives us an ability to understand our boundary conditions later on. I'm gonna call this starboard wall outlet. Fourth wall. So you can see the walls of our virtual wind tunnel are all here. Then we have an inlet and an outlet. So just like our previous version, we have to do a Boolean operation, and I'm going to do a subtract. The idea here is I subtract both parts, and I'm going to have a target part of the block. So what it's going to do is take this part and chop out volumetric domains of any other parts. So I'm going to do this based on the CAD and based on and force it to happen now. And it created this subtract domain. So I'm going to go to, so since I'm in this geometry scene, I can come here and manipulate some of these features. I'm going to select a part. I'm going to move from a sphere, and let's look at the subtract part and see what happened. So this is our subtract part. You can see we have access to all the boundaries. I'm going to select this thing, and what this does is kind of makes it translucent, so we can see the sphere in the middle. So now we're there with the parts. What we do is we assign parts to a new region. Again, each part surface and each part curve, we want that. So when it generates our region, we have boundary conditions, boundaries that align with our boundary conditions. Here, I'm going to turn this into an inlet. Again, I'm just going to use a velocity inlet. Here, I'm going to use a pressure outlet. I'm going to make all the tunnel walls symmetry planes for simplicity. And I'm going to leave this as a wall. Once we're at this point, we can start making a mesh. So I'm going to right click on operations, go to new, go to mesh, and do an automated mesh. I'm going to apply it to this subtract. You have to have it attached to a region if it's going to work. And I'm going to use a few different things. I'm going to use a surface remesher. It basically remeshes the surface. If you don't use this, it'll take the CAD representation. You're going to do repair. Let me use this trim cell and a prism layer mesher. Come here. This is basically how it remeshes the surface. This is how it remeshes the trimmer. And this is a prism cell or layer mesher. This is this base size. So it basically tries to have a representative cell size that's 1. So basically we're assuming a reference size that's similar to the diameter of the sphere. I'm going to do a couple things different than what I did in the previous time. I'm going to keep this at 0.1. I'm going to make this 64. I'm going to make 31 prism layers. Thickness of, well, a lot of these are actually similar to the one before. One thing I'm going to do in 3D, they have this max cell size. I like to fix this to 100. I don't like things growing. And so I'll show you that later. Okay, plus so now we have all the meshing parameters, and that we're actually ready to mesh. So I'm going to mesh, and we'll take a quick look at how to interrogate it. It's a little bit different in 3D. So if I come to the mesh option, what I see is this 3D mesh. I could select this, I could hide it, and then I just see a 3D mesh inside. And I can only see the surfaces because we cannot plot the domain. So in 3D, we have to do something a little different. We go to this derived part, right click, and I typically use sections. I'm going to make a plane. And if I zoom out, you see this plane, it's cut right to the center. What I want to do is make the origin here, make it at 0, 0, 0. And kind of the ideal plane is to be plotted in the Z normal plane. So you can see it cut. And the idea here is it will cut through the mesh and generate a picture that we can look at. So I'm not going to add a displayer for now, but what I can do is click here, drag it in, and put it with the mesh. And now we can see, again, you can see how it's a cut through the center of the domain. We could see what the mesh looks like. So I told you we could do this maximum cell size. So it defaults to something like 10,000. When we do this and generate the mesh, what it does is it puts the surface size here and here, but then in between it allows it to grow to these enormous values. And typically you want your cells to be the largest on the outer domain and the smallest near the body. So it's kind of inconsistent with what a nice mesh might look at. So one of the easiest things is to do is to work outside and set mesh sizes on the outside and then kind of force your way inside and refine as you go in. So now we need to go to the physics. So we'll start off steady, go to gas, segregated flow, constant density. Let's stick with laminar or turbulent, scalar Mares. And this is basically, the bulk of that. One of the things we need to do is set our boundary conditions. So recall that our boundary conditions were 20 meters per second. From there, set that 20 meters per second. These are all walls. So we don't have to worry about that. This is a wall. We don't have to worry about that. And this is an outlet. So it's right here. So we just set pressure. Again, it's gauge, so it's 0. That's kind of it to get things running. But we want to do some diagnostics. So I'm going to make one thing I'm going to do is I'm going to hit this button. It initializes the flow to whatever you have initial conditions set as. So these. And I'm going to go here and look at a scalar scene. And we kind of have a representation of things. But what we want to do is kind of gauge this in a way that we can actually interrogate. So I'm going to come here to the parts and just select that plane that we cut through there. And I'm going to set this to an velocity. Look at the velocity magnitude, similar to before. So we have a velocity of 0, which is consistent with our initial condition. We might want to set that to 20. And if we do so, we get a clear solution and then just reinitialize. It goes to 20. Okay. Another thing we might want to do is go to our boundary and grab, for example, our sphere, drag it in here. And I'm going to make a new scalar scene associated with that. You get this new option. I'm going to right click here, and I'm going to look at pressure coefficient. So I'll hit OK. So there's a tricky thing about pressure coefficient. When you go to Tools, Field Functions, and you move down to pressure coefficients, and you have to just set this. So our reference there, you have to set these up so we know what the pressure coefficient is. There should start as. So our reference density was in our models, gas, air, material properties, density, constant. So this is our density. So that, and we set a reference velocity of 20, and that's it. And you should start getting a pressure coefficient. I'm going to, again, make a report. I'm going to make the report as a, where is it? Force coefficient. And I'm going to make it a 3D drag coefficient. It's going to be in the positive X direction. I'm pasting in that same density. Our velocity is 20 meters per second. This time, our area is going to be something slightly different. It's basically pi times 0.5 squared, which is, the area that's consistent with the sphere. And that's pretty much it. Similar to before, I'm going to create, monitor, and plot report. And as we run it, we'll see residuals come down, we'll see solution evolving, and we'll see a drag coefficient history. So here's our residuals. You can see things are running a little bit slower than before. It's because it's 3D, you have a lot more cells. We go to our drag coefficient, nothing's coming up. I'll show you why in a second. And if you look at your solution, you can see a flow over a sphere. Okay, let's fix this. Why is the drag coefficient not there? If you click here, if you recall, I forgot to select a part. And I forgot to select that the sphere was there. Run this one iteration, you can see it already comes up. Now we can start tracking our convergence history. We can start visualizing what the flow looks like. Similar to before, I'm going to go to the scene and make these smooth profiles so things look a little cleaner. It's nice to have the other one for debugging, but smooth is more visually interesting. Here's our residuals. You can see things are kind of converging. That's converging. This is kind of evolving. Okay, so I'm going to show you one more quick trick. And I think that we're good here. So here we can see that we obviously have wake, and look at how many cells we have. Right here, it's a reasonable amount of cells. Here it's kind of getting worse, and worse. And we don't have the ability to resolve the wake. And you need about 20 cells, just like you need 20 time steps for a convective length, you need about 20 cells to resolve any kind of feature. So what we can do is go back to the meshing land. So we're looking at automated mesh. There's these options here called custom controls. So one thing we can do is create a new part, and I'm going to create a cylinder. And I could actually do this in the context of this. Actually, I'm not going to do the cylinder. I'm going to create a cone, and I'm going to lock in this position so it fits there. And give it a starting radius of 1, and then we can come to, hold on, this position, and I can move these to, let's say, 5. And 0, 0. So we have this cylinder or a cone, and I could even expand things to a radius of, say, 2. Here, maybe it's 0.5 or 0.6. So what we have is this region here. I'm going to create it. And if we take a quick look at it, what it is a region here where we could actually say, hey, I want more mesh in this region. So because volumetric control, I select that part. And I can either decide to remesh, to add a prism layer, but here we want to change the actual trimmer. We make here I'm going to say an anisotropic. So isotropic is saying I want them all to be the cells to be nice, kind of like rectangles, not rectangles, squares or cubes. With this, I could make them a little more complicated in shape. So instead of being 1 meter, this would actually aim to make it something like 0.2 meters in the x direction. 0.1 meter in the y and 0.1 meter in the z. If I remesh, one of the nice things about Star is you kind of tweak these mesh parameters, agree meshes, and then interpolate your solution to it. And now what we see is we have a much nicer mesh in the wake. And as we evolve the solution, it doesn't diffuse the wake and it tends to grow. And we have a better approach to track complicated features. So if you look at the residual, you can see these bumps that's associated with remeshing, and things are going a little bit different, but not horrible. In general, it seems to be a reasonable goal type solution. If this is not consistent with one thing you have to be careful of is your drag coefficient. If you're comparing with theory or a base value, make sure you defined the drag coefficient in a way that's consistent with however it's reported. If you're looking at the solution, one of my general feedback from this would be, okay, this is probably too big. I could probably add more mesh in just this region to really push this out. And this is more or less, the general, I think, differences in the 3D, and I think it highlights them. Okay, just as again, a recap, we created a outer domain boundary, a solid boundary. We did the cookie cutter thing to here and here to get the overall result. The flow domain, the fluid domain. We specified the regions and specified the boundary conditions, and we came into the meshing process, remesh and developed a mesh. We established the physics. We created this plane where we could actually start seeing things. And then we created reports, and we were able to get what I think looks like a pretty reasonable solution. All right, that's pretty much it.